All right, so let's draw the shear force and bending moment diagram for these two. Again, I'm going to help you out, and I'm going to tell you that the force, the reaction force on the left side is P over 2, and the reaction force over here is also P over 2. No moments. Now, a force up on the left side, is that positive shear or negative shear? Positive. So we're going to start off at P over 2. A force up on the right side, is that positive shear or negative shear? Negative. So we're going to end at negative P over 2. And we know that the change in shear, oops, I get the wrong one. The change in shear between any 2 points is the area under the load diagram. I also notice I got this load P here, so I'm going to subdivide my section up so that I can deal with the load to the left and then the load to the right. So looking at this first section, the L over 2 section, what is the loading from 0 to L over 2? 0. So the area under that curve is 0, so there's no change in the shear. So if I start at P over 2, I should end at P over 2. And the slope of my shear diagram is equal to the load. So let's see. The slope of the curve here should be equal to the load. The load is 0. So here's my curve with 0 slope. So I now know I have constant shear over the first section. We also know that for a point load, the change in shear is equal to the load. That load is what? Positive or negative? Negative. So that means that I go from the left side to the right side, my shear should change negative P. So here's positive P over 2. I cross over, I should hit negative P over 2. The change in shear between these 2 points seems to be nothing. Is that true? Well, change in shear is equal to the area in the load curve. The load curve here is 0. No change. So that's right. And the shape or the slope is given by the load. The load is 0. So here's 0 slope. So there's the shear in the beam. Where's the maximum shear occur? Okay. For shear, positive is not bigger than negative. It's just direction. So it seems this beam everywhere has a shear of P over 2. And this little weird area directly under the load, we don't even know what that is. That's the shear flip-flopping from side to side. The shear changes direction. This would probably not be a good place to put a connection. All right, what about moment? What's the moment, starting moment? 0. What's the ending moment? 0. All right, so we know the change in moment between any 2 points we like is the area under the shear diagram. So looking at the first section, 0 to L over 2, what's the area under the shear diagram? What's a rectangle? Has a base of L over 2, has a height of P over 2. So that's a value of PL over 4. And that's a positive area. So I should end up at positive PL over 4. And what's the shape of this curve? Well, we know that the slope of the moment is equal to the shear. What's the value of the shear everywhere in that region? Positive and constant. So here's a positive, constant slope. In fact, if I asked you what the slope here was, you would say that it was P over 2. Now from L over 2 to L, that change in moment is equal to the area under the shear diagram, under that same range. And what is that area? Yeah, it's L over 2 times minus P over 2, so that's minus PL over 4. Positive PL over 4 plus a negative PL over 4, 0. And the moment, slope of the moment is the shear, and the shear in that section is constant and negative. And for this particular problem, that would be minus P over 2. So there's your moment diagram. Where's the maximum moment? It occurs at L over 2. What is that value? PL over 4. Is it positive or negative? Positive. You get a lot of information from your diagram once you construct it. If you've ever seen a beam that got deeper in the middle and then went tapered back off on each end, that's because the load looks something like this. You got maximum moment in the middle, so you want a lot of capacity, and you want it to go down to lower capacities at the end. So you see a lot of structures that kind of tapered in the middle if they're supporting a big point load. All right, one down, one more to go. Let's go over to this guy. I'm going to, again, shortcut you a little bit and tell you that this load over here is going to be W0 L over 2. And this one will also be up W0 L over 2. What's the moment at this pin? 0. And the moment this roller? 0. So that means I'm going to start, when I draw my shear diagram, I'm going to start off at, what kind of shear force is this? Positive or negative? Positive. So I'm going to start off at positive W0 L over 2. What kind of shear force is this, positive or negative? It is negative. So I know where I'm going to start. I know where I better end up. The change in shear, wrong one. The change in shear is equal to the area in the load curve. So what's the area of the load curve here? It's a rectangle. What is that? It's base times height, so that's W0 L, and that's acting down, so that's a negative area. So if I start off at W0 over 2 and subtract W0 L, I do get negative W0 over 2. So that's great. And what's the slope? What's equal to the load? And what's the load? Constant and negative. So here's a line with a constant negative slope. And now I have positive shear going down to no shear and then increasing to negative shear. So what's the maximum shear in the beam? W0 L over 2. Where does it occur? At either end. We don't care about sign. Sign is just direction. Now what's happened is, you see, I've now created a situation where I've got like a little positive area triangle and a little negative area triangle. And for this particular load, it happens right in the middle. For some of our loads, we're not sure where this 0 is going to happen. You'll have to find it. But you do know that these triangles have to be similar. So this height to this length have to be equal for both. And since they both have the same height, they both have to have the same length, and the length has to add up to L, so they have to be both WL over 2. So we're going to work some problems later on, probably not today, probably next Tuesday, where this doesn't always cross over right in the middle. You'll have to find that position. But today it was easy. So what's our starting moment here at the left side?
W not L squared over 4?
No, it is 0.
Like what?
The moment.
Oh, okay.
And what's the moment here? 0. The change in moment is the area of the shear diagram. What's the area of the shear diagram right here? Well, that's a positive area. 1/2 base times height. So that's going to be W L squared over 8. And that's positive. W not L squared over 8. And what is the shape of the moment diagram? Well, it's equal to the shear. What is the shear value at the starting point? It's positive. So here's my positive slope. And it decreases to 0. So this should have a 0 slope. So I'll connect those two. I'll get a curve that looks something like that. Now from L over 2 to L, the change in moment should be the area of the shear diagram. And what's the area of the shear diagram from L over 2 to L? Well, it's a negative area. 1/2 base L over 2 times height negative W naught L over 2. You get negative W naught L squared over 8. And that does bring you back to 0. And now the slope is equal to the shear. You look at the shear value starting here. It's 0, so 0 slope. And it decreases to a maximum value of that, which is a negative slope. And you sketch it in. You get something like that. So that's a parabola.
So why is it W naught L squared over 8?
It's on the area.
So where's the maximum moment? Right in the middle. And there's the value. You might remember, this is a kind of a classic formula for the maximum moment for a simply supported beam, WL squared over 8. A lot of people who do a lot of structures, they've just memorized that, WL squared over 8. I don't expect you guys to do, but you can easily derive it. Any questions about that one?
Oh, because 1/2.